Well, I'd like to thank to the organizers for the possibility of being here celebrating Adolfo. I'm very grateful to Adolfo for his hospitality and care while I was staying here in Mérida. So thank you, Adolfo. And I'm going to speak about the geometric classification of Lie superalgebras. This is a joint work with Isabel Hernandez here from CIMAD. So all the questions to Isabel, please. So, what was our motivation? Recently, many people have been studied the geometric classifications of different structures, such as Lie algebras, Jordan algebras, Malchev algebras, superalgebras, but we found nothing about Lie superalgebras, so we wanted to give it a try. So, what is a geometric classification? Well, you begin with an algebraic classification. Yes. So, for every Lie superalgebra or every object, yes, you consider an element, and all the other Lie superalgebras are isomorphic to this, give us the whole orbit of the Lie superalgebra. So we know what happens in the orbit, but we want to know what happens in the closure of the orbit. And it turns out that in the closure of the orbit, more specifically in the frontier, there are another Lie superalgebras with their orbits. So the algebraic classification gives us these orbits, and we want to understand what happens with the closure. So for doing that, we need some invariants. So we can say this Lie superalgebra lives in the frontier of the orbit of this other Lie superalgebra. Using this invariant, we can discard these possibilities. After we discard which Lie algebras don't live in the frontier, we want to prove that the remaining Lie superalgebra lives in the frontier. So, in order to do that, we use degenerations, and once we complete that, we obtain the orbit closure for every Lie superalgebra, and this gives us the irreducible components in the variety. So, a geometric classification is finally gives all the irreducible components in the variety. So, what is a Lie superalgebra? It's a C2 graded algebra with a bilinear map satisfying these conditions, the super skew-symmetry, the super Jacobi identity, as usual. And a Lie superalgebra morphism will be a linear map between the Lie superalgebras, preserving the bracket and preserving the gradient. So, what is the variety of Lie superalgebras? We fix a supervector space of dimension mn and fix an homogeneous basis in that form, and we can think of a Lie superalgebra defined in B, such as a set of structure constants in CM3, etc., where the structure constants are given by these coefficients in the composition of the brackets. So, since if we consider the set of structure constants, this structure constant must satisfy polynomial equations, the ones given by the skew-symmetry and the super Jacobi identity. So we can say that the set of all Lie superalgebra of a fixed dimension is an affine variety in this space. So to that variety, we denote it in that way. So I said that we needed first an algebraic classification, and then we needed invariants. So, in this variety, we have a group acting, this group, which is isomorphic to GLM plus GLN. And this group acts by change of basis, and the set of G orbits of the action is in one-on-one correspondence with the isomorphism classes in the variety. So, we say that a Lie algebra G degenerates to a Lie superalgebra H if H lies in the Zariski closure of the G orbit. Yes, and in this case, G degenerates to H. And an equivalent definition of degeneration is given by this lemma. If we have an operator, GT, such as the limit of GT acting on G is equal to H, then we say that G degenerates to H. So we can move continuously from G to H. And we will say that Lie superalgebra is rigid if its orbit is open in the variety. So, what were the invariants that we use? What you do here is you choose or use different sets, which you prove that they are close, and since they are close, you get some relations that a degeneration must hold. So the relations are this: the dimension of the orbit of G must be greater than the dimension of the orbit of H. If gamma of G, gamma is the commutative part. If gamma is 0, then gamma of H must be 0, and so on. So dimension of the derivative algebra must be greater. The dimension of the generalized derivations, alpha, beta, gamma derivations, also must be lower. And we have also this invariant. So in general, these are invariants that can be used for many other structures, for Lie algebras, pre-Lie algebras, etc. So these are known, but for us there wasn't enough, so we couldn't discard the generations just using this, so we needed more invariants, so we defined these two. We define a Lie superalgebra called the abelianization, in which we keep only the commutative part, only the abelian Lie superalgebra, and we define the forgetful Lie superalgebra, which is just the gamma part we annihilate. And it turns out that if G degenerates to H, the abelianization of G degenerates to the abelianization of H, and the forgetful of G degenerates to the forgetful of H. So this was helpful. Another invariant that we use is the so-called IJ invariant. So which is a nice invariant for non-nilpotent structures. It works very well. So it turns out that if G degenerates to H and the IJ invariant exists for both Lie superalgebra, then the two Lie superalgebra have the same invariant. So with all this, we could discard possible degeneration. So, well, what we exactly do, we consider Lie superalgebras, complex Lie superalgebras of dimension 2, 2, and we obtain the algebraic classification, which gives us 21 families of Lie superalgebras. We have a few with a parameter, one with 2 parameters, others with 1, yes, and 2 more with 1 parameters. So after obtaining this, which was hard work, we begin with our study of the possible degeneration. So using the invariants mentioned before, as an example, I draw here the non-possible degeneration. And after we discard all this degeneration or non-degeneration, we have to obtain the degenerations. So as an example, I put 4, there are many more. So what we do is to obtain the GT morphism. So these are examples. Well, and once you have all this, you can draw the Hasse diagrams. So in here we have this Lie superalgebra degenerates to this, to 4, to 20. Lie superalgebra 14O degenerates to 13O minus 1, to 2. 2 degenerates to 3, and 3 degenerates to 0, which is the all 0 brackets. So I draw every branch of the complete diagram because it's very messy to draw it all in just one draw. So what we obtain is that these Lie superalgebras are the ones that are not a degeneration of any other of the Lie superalgebra. So we obtain these branches, this one, this one, this one, and this one. So there are many branches. So it turns out that from here you can see the orbit closure. So here, if we read, the orbit closure of 19 alpha is given by the orbit of 19 alpha, the orbit of 13 alpha, alpha plus 1, the orbit of 11, and the orbit of 0. So from this diagram, you read the orbit closures. So it remains to find the irreducible components. So it turns out that the irreducible components of every variety of Lie superalgebras are closures of single orbits or closures of an infinite family of Lie superalgebras, of orbits of Lie superalgebra. So first we wanted to obtain the ones that are closure of a single orbit, and to do that we compute the second cohomology group to obtain the rigid ones. So it turns out that these 3, 19 minus 1, 1, and 5 are rigid. The first one that I show. This is rigid, and this is rigid. So every one of these gives me an irreducible component. So at least we have 3 irreducible components. And this one has a particularity. LS1 is an nilpotent Lie superalgebra. So it's an example of an nilpotent Lie superalgebra which is rigid. And that thing doesn't happen in the case of Lie algebras. There are no rigid nilpotent Lie algebras. So it's, well, it's curious. So it remains to find the ones that are closure of infinite families. So in order to do that, we consider the following lemma. If we have a Lie superalgebra and a family of deformations of the Lie superalgebra, then the Lie superalgebra G lives in the closure of the union of the orbits of every deformation. It's like saying that G is a degeneration of all these Lie superalgebras. So we obtain that the Lie algebra 7 and 17 minus 1 over 2. Well, wait a minute. We proved that these were rigid, so it remains to see what happened with all these. All the ones in the top. This one, and this one. So we proved that number 7 and number 17 deform to this Lie superalgebra and this family of Lie superalgebra for almost every alpha. That 8, which was one of the top, deformed to 16 and 15 for alpha, almost every alpha. That 9 deforms to 20 and 19 alpha. And that all of these, that depends on 2 parameters, deform to 6 for all gamma. And 17 alpha also deforms to every one of these. So with all this, we can, and using this lemma, we can give all the irreducible components of the variety. We have the 3 ones given by the rigid ones, the one given by a single orbit, and the ones given by infinite families of Lie superalgebras. Okay, thank you. Thank you. Yes, we use some computing. Yes, I use Maple to program many things, many of the invariants.
How much do you know of
The study, it must be like the same. I mean, we can use degenerations defined as a morphism, and
have you tried some? I mean,
no, we started with complex number. I guess no. No, we started with complex Lie superalgebra. We haven't really seen the case of real Lie superalgebra. Maybe for an expert.